So this is going to be Learning and Memory Part 2. We did Part 1 last week where we just basically looked at memory. Today we're going to look at learning. So when we start by looking at this, we have to define what learning is. So learning is going to be essentially just the process of acquiring new information. It's going to be how we, in our brain, how the brain changes to new experiences. So if memory is our ability to remember episodic memory, semantic memory, all of those different types of memories, learning is a type of memory then, but it's going to be a type of memory that's related to our ability to do things. And so we're going to look at it mostly in this set of slides as basically these long-term changes to the nervous system when it comes to learning. So we'll look at things like classical conditioning, operant conditioning, and see what's happening there. So you've still got the same process, the encoding to consolidation to storage to retrieval. But now we're going to look at what goes on with that encoding side that allows us to basically, what happens with the wiring in the brain. There's going to be 4 different types of learning we're going to look at. There's the stimulus response, motor learning, perceptual learning, and relational learning. I could talk about those more right now, but I have slides for each of these. Let's get to the first of those. So stimulus response learning is essentially our ability to perform a particular behavior when a particular stimulus is present. So it's when we're given a stimulus in the environment, how do we respond to that stimulus? And this is where the brain is basically forming connections that are making associations. It's making these associations between the stimulus and the response. And the 2 different categories for stimulus response learning are those 2 typical ones when it comes to learning: operant conditioning and classical conditioning. And we'll look at each of those in detail, but you should know them for the most part from other classes. So again, stimulus response is there's a stimulus in the environment. What is your response? And when you're looking at that, how is the wiring in the brain working or being rewired so that you get this response to this stimulus? The first of those 2 is classical conditioning. So just a quick refresher on classical conditioning. What it is when you have an unconditioned stimulus. So whatever the unconditioned stimulus is, let's say you've got, for Pavlov, you've got the food is the unconditioned stimulus that causes an unconditioned response, salivating. So in Pavlov's dogs, it's the food is the unconditioned stimulus. The salivating is the unconditioned response. Then it becomes paired with a conditioned stimulus, so a new stimulus. The conditioned stimulus could be ringing a bell. Ringing the bell that you pair with the food. You pair that enough times, they become paired together, and now the conditioned stimulus, even in the absence of the unconditioned stimulus, will cause the response that is now classified as a conditioned response. So in that case, if you ring a bell every time you feed a dog, ring a bell every time you feed a dog, well, normally a dog salivates when you feed it. You can get to a point once you've done it enough times that you can just ring the bell without feeding the dog, and the dog will start salivating. So in that case, like I said, the ringing of the bell becomes a conditioned stimulus, and the salivating is now the conditioned response instead of the unconditioned. Conditioned means it has been paired. Now we're going to use a Eyeblink example in just a minute and show how this becomes paired neurally, but this is the basic classical conditioning. However, something you don't normally hear in intro and other classes is Hebb Rule. Hebb Rule is going to be something that's more neuro-based because it's talking about basically the cellular basis of learning. So the Hebb Rule says that the cellular basis of learning involves strengthening of synaptic connections that is repeatedly active when the postsynaptic neuron fires. So it is essentially saying that the neural connection becomes stronger over time if they are firing at the same time. So that goes back to what is happening with classical conditioning. Well, classical conditioning, you're pairing two different things together. Well, the Hebb Rule says that when you've got those two different neurons firing at the same time, when they're connected but they're firing at the same time, that connection actually becomes stronger. So the activating of the two neurons that share a synapse. So you've got two neurons that share a synaptic gap at the same time, and the synapse that connects these two neurons becomes stronger. And the quote from Hebb Rule is that neurons that fire together wire together, because the more times that they're firing together, the stronger that connection becomes. It can start out as a very weak connection, but firing over and over again will eventually strengthen that connection so it becomes just as strong as strong connections in the brain. As I said, I'm going to use an Eyeblink experiment here as an example that we're going to look at. And this Eyeblink experiment is where you get a puff of air in the eye that causes a blink. The puff of air causes the blink. So the puff of air is the unconditioned stimulus. The blink is the unconditioned response. However, start pairing that puff of air with a tone. So 1,000 hertz tone, by itself, the tone does not cause a blink, but you pair that tone with the puff of air, and eventually that tone will cause a blink even in the absence of the puff of air. So that tone becomes the conditioned stimulus. The blink is now the conditioned response. And as you see here, you've got the puff of air going to the blink is a strong connection. It's a already basically hardwired connection. That puff of air is going to cause a blink. The tone to the blink is a weak connection. It doesn't normally cause a blink. But through repeated pairing of the tone and the puff of air, this weak connection between the tone and the blink becomes a strong connection. So the strong connection now causes the tone will cause the blink. So when we're talking about classical conditioning, like I said, everybody should know what classical conditioning is and operant conditioning because they're talked about in most psych classes. However, what is actually going on in the brain when we're talking about classical conditioning? Well, this is what's happening. That as the two are paired more and more, the association becomes stronger, and then just one firing will actually release enough neurotransmitters into the synaptic gap to cause the response. Does that make sense? As far as what is going on in the rest of the brain, well, the amygdala is important to classical conditioning, especially for when we're talking about aversive stimuli, since aversive stimuli produce a variety of effects. Pairing something with these aversive stimuli basically strengthens connections in the amygdala. So the information about the conditioned stimulus and the unconditioned stimulus that converges in the lateral nucleus of the amygdala, and this is where that connection becomes stronger. And then the somatosensory input that's coming in will then activate the stronger connections that have been paired and made. They activate the stronger connections, the strong synapses in the lateral nucleus. So if we're talking about where all this is going on in the brain, especially when we're talking about things that have been paired with aversive stimulus, such as that puff of air, that's an aversive stimulus. When they're talking about things paired with that, and these tend to be the ones that are paired the strongest, it is being paired in the amygdala. Then we've got to look at how glutamate results in this, or what goes on with glutamate, and this is where we're going to first talk about long-term potentiation. We're going to talk about it more at the end of this, so we're going to kind of briefly hit on it here and then talk about it in much more detail later. But long-term potentiation is basically an increase in the excitability of a neuron to a particular synaptic input caused by repeated high-frequency activity of that input. So essentially, the more activity that occurs, the stronger that connection becomes. It's something I've said a few times. But when we get to actually what's going on with long-term potentiation, one of the things we'll look at is how when the neuron's firing and when that connection occurs and how all of that integrates together to actually strengthen this connection even more. So, but the big thing is that glutamate is going to be what's responsible for long-term potentiation. Glutamate it pairs with the receptor neuron, the postsynaptic neuron. And it pairs with the postsynaptic neuron in such a way that it actually can create more connections. And that it'll create more receptor sites. And the more times that glutamate is pairing in a specific circumstance, like I said, we'll talk about that later, but the more times glutamate is pairing or binding to the receptor sites on the postsynaptic neuron, then the more glutamate sites that actually show up. And the more glutamate sites that show up, the more it pairs. So it becomes a snowball effect that the more times this gap is fired into, the more times the stronger that connection is going to become as a result. So as it says here, synaptic changes in the glutamate system increase the excitatory postsynaptic potential to the postsynaptic cell. And we'll talk about the exact mechanism that's going on there later. And there's actually certain circumstances where it can even becomes even stronger. Let's transition then into operant conditioning. Everybody should know operant conditioning as well. Operant conditioning is going to be basically when you're looking at reinforcement and punishment. If a behavior is reinforced, it increases. If a behavior is punished, it decreases. And then there's positive and negative for each of these. You can have positive and negative reinforcement. Positive and negative doesn't mean good or bad. Positive and negative means the addition of something or the subtraction of something. So positive reinforcement is the addition of something wanted. If you do good, get good grades, you get rewarded with money. That's a positive reinforcement. You're adding something wanted. A negative reinforcement is the subtraction of something unwanted. You bring your grades up, you get your phone back, or you get ungrounded, or you get to go out and see your friends. That's an easier one. You get to go out and see your friends when you get your homework done. So it's a negative reinforcement. The subtraction of something unwanted, the unwanted thing would be being stuck in the house. And you could even say that there's really positive reinforcement going on there too, because you're allowed to do something you want to do, but the negative reinforcement is also there. Then punishment is the other side of it. So this is going to decrease the behavior. So positive punishment, again, doesn't mean good punishment. It means the addition of something unwanted. Like the kid being grounded for doing something wrong. So positive punishment, the addition of something unwanted. Negative punishment is the taking away of something wanted. So got a teenager and you take away their car. So the taking away, negative punishment would be the taking away of something wanted. And again, they're interrelated. You can see both sides of both positive and negative punishment at the same time. Okay, that's operant conditioning. Let's look at operant conditioning though in the brain. So it takes place mainly in the basal ganglia. And the circuits here basically is where you're getting the sensory association cortex is pairing with the motor association cortex. And there's going to be two major pathways we're going to talk about here. The direct transcortical connections and the connections that are in the basal ganglia and thalamus. Let's start with the transcortical. So the transcortical pathways are the pathways that are, when we talked about memory, these are the ones mainly involved in things like episodic memory and then complex behaviors that involve deliberation or instruction. So when we do something complex, like learning something new, so when we're learning to ride a bike, we're activating the transcortical pathways because we are doing something deliberate and we are learning it. So what's going to happen is you do this over and over again enough, and this basically deliberate instruction becomes a memorized script to follow. So riding a bike is a good example there. You get on a bike, the first time you're learning to ride a bike, you have to learn how to do balance, you have to learn how to pedal, you have to learn how to hold your hands, you have to learn how to do all that, and you have to effortfully think about every single step of that, which is why it's really hard at first. Then you do it enough times, you do it repeatedly, and this transcortical pathway is activating repeatedly, and eventually it becomes intrinsic. Then after that, it goes into the basal ganglia pathway. So the transcortical pathway is where you're deliberately learning it. It's that early stuff. Then once it becomes hardwired, once it becomes effortless, or less effortful, once it becomes automatic and routine, it is transferred to the basal ganglia. And this frees up those transcortical circuits, because those transcortical circuits, we've only got so much we can use at a time. We can only focus our attention on so many different things. When we're talking about anything that's effortful, anything that involves concentration, anything that involves active thought, our brain can only do so much at one time. So there's a limited amount of transcortical space available, in a sense, is a good way to say it. As we learn these behaviors and they become automatic, and they become that paired, and it can be through, again, any type of reinforcement, punishment, however either of those are occurring, the behaviors start to become more automatic. We don't have to think about it. Let's say we're talking about having a kid do chores. Let's just say dishes. At first, you have to teach them how to do the dishes, and you have to reward them for doing dishes or punish them for not doing it. Rewarding is always better, so we'll use that as an example. You reward them. Next day, you instruct them, you reward them. Next day, you instruct them, you reward them. Eventually, if you've paired it well enough, because they're using the transcortical early on, if you've done it well enough, it'll get that behavior will then be in the basal ganglia pathway, and it'll be automatic. They won't have to think about doing it anymore. If you have them doing it at the same time every day, they'll start doing it at that same time without even being instructed, without even really having to think about it. It becomes an automatic process. Does that make sense? So let's talk about reinforcement specifically, because reinforcement is going to talk about, we're going to look at the dopaminergic, I can't even say it, dopaminergic, yeah, that's not even correct. I just can't even say it today. But you get what I'm trying to say. It's the dopamine pathway. And the dopamine pathway is the one that's responsible for reinforcement, which is why reinforcement works better than punishment. We've got this perception in general that punishment works just as good as reinforcement, but it doesn't. Reinforcement works better because reinforcement activates the reward system pathways in our brain, and the reward system pathways in our brain actually then will form stronger connections. So whenever we're reinforcing a stimuli, basically these dopamine pathways are activating, and these dopamine pathways that are activating the prefrontal cortex, it's providing input to the ventral tegmental area, and it's basically releasing dopamine so that we receive pleasure or satisfaction or happiness from this connection. And we try to seek out more pleasurable connections or things that induce happiness, things that induce satisfaction, however you're going to look at it with that dopamine pathway. So we tend to increase the behaviors that have been paired with this. This is also why it's so easy to get addicted to drugs that activate the dopamine pathways. So what it's going to come down to is the mesolimbic and the mesocortical systems. These are the ones that are going to play a role in reinforcement because these are the ones that basically the dopamine pathways work through. All right, let's switch to motor learning. So motor learning is the next one. And motor learning is going to be whenever we're establishing a response or changing a response within the motor systems following the stimulus. And this requires sensory guidance from the environment. The motor system isn't going to activate without input from the environment. And the main area is going to be the cortex. Now, one thing I'll say is that we skipped the chapter where motor movement was involved in that. So a lot of the things that are going on in the brain involved with motor movement we haven't discussed. And I'm not going to go into those here. I'm not going to make that a requirement to know all of that for this. So when we talk about motor learning, we're just going to basically talk about it as an overview real quick. We're not going to get into it simply because that's one of the chapters we skipped because we don't have time enough to cover every single chapter in the book. But it's going to be basically many different areas of the cortex that are going to involve learning movements. And much like when we were talking about the way operant conditioning works, it works in a similar way. That's the easiest way to explain it. It works in a similar way in that the early connections are deliberate, and then when they become effortless, when they become where we don't have to think about it, these are connections that basically become hardwired. And one interesting thing about motor learning, and this is true for sports, so those who participate in sports, this is one of those things that's really, I guess, an interesting thing and something to take into consideration. That is that we know motor learning actually occurs in part between learning sessions. So let's say you learn a new behavior. You're doing Let's say you're learning some martial art, Taekwondo. Let's just say Taekwondo. You're learning Taekwondo, and you're learning a new move. And in practice, you do this move. And you have rapid learning that occurs while you're in practice. If I test you right after practice on that move, you'll have a certain amount of competence. If I test you a day later, you'll actually have more competence than you did at the end of the session. That is because we continue to learn these things between training sessions. We would continue to learn these things, especially when we sleep. It aids in memory here. So learning to do various different motor movements, and it's not just sport that does this, it's going to be anything where we're talking about motor movements. Learning different motor movements actually increases over time between training sessions. Just one of those really interesting things about learning motor movements. And it's just like memory of events and things like that, how they become consolidated over time, especially when we sleep. So when you're studying how important sleep and actually spacing it out is, it becomes a similar thing for learning motor movements for when you're talking about sport or anything like that. So when we're talking about motor learning, we also have to look at the basal ganglia, just like we looked at it for stimulus response learning, and how basically when you have damage to the basal ganglia, it can lead to difficulty in learning these automatic things. So both Parkinson's and Huntington's result in damage to the basal ganglia. And this damage to the basal ganglia actually results in difficulty in learning motor movements. So those with Parkinson's or Huntington's have, besides the fact that they might have different tremors, different difficulties in movement, period, they have a much harder time learning specific new movement things. So if they tried to learn something relating to like yoga poses and things like that, that it would be more difficult for them to learn because of the fact that their basal ganglia is damaged. Any questions there? Okay, let's switch to perceptual learning then. So perceptual learning is basically going to look at, can you recognize stimuli that have been presented before? If you walk into a room, do you recognize the people that are in the room? If I show you pictures, do you recognize things in those pictures? Stuff like that. So its primary function of perceptual learning is to identify and categorize objects and situations, and to categorize and identify them quickly. And essentially this is where the sensory association cortex for each sensory system is working. Now when we talk about perceptual learning, we're usually talking about vision, but we have perceptual learning for all of our senses. So let's say sense of smell, being able to recognize a smell. If I give you a smell of lavender, all of us should be able to recognize that that's lavender because you've likely experienced it enough before, and your perceptual learning has learned that that smell is lavender. Vanilla is the same way, some of these very common smells. But then there's uncommon smells that you can learn, but not everybody necessarily knows. Sounds, you learn to identify whose voice it is, things like that. So all of our senses do work with perceptual learning, even if we typically use examples of vision. We're talking about being able to recognize faces in the fusiform facial area. So that's where perceptual learning occurs for faces, is in the fusiform facial area, things like that. So when it comes to the cortex, information from the thalamus is sent to the extrastriate cortex, then to the visual association cortex. When we're talking about vision, again, all of them work in a similar way, but essentially this information is being sent on, and then that visual association cortex, if you recall, just like all of the other ones, for the other senses is split into two. But for vision, it was the ventral stream, which is the what, and the dorsal stream, which is the where. When we're talking about perceptual learning, it's that ventral stream that is activating, the what. And those connections, again, once we see things, we form connections to the what, so that we can identify when we see things or people. It's always interesting to me how the differences in that ventral stream, especially like the fusiform facial area, are between people. How some people easily, and not even talking about that person I knew that had damage to that region, but how some people easily remember faces and some people don't as easily. But at the same time, you've got the opposite as well, where some people easily remember names and other people have trouble with it. I rarely forget a face, but I'm so bad with names that I can't remember anybody's name. I have almost stopped trying to remember names because I'm so bad with names. But faces, I could, there's somebody that I saw 30 years ago that I could see again and be like, oh, I know you, that type of thing. So it's just matters how strong these pathways are for you in these regions of the brain. When it comes to perceptual learning, the cortex and memory is very important because it's, again, how these neural circuits become wired when you've got the same stimulus being presented over and over. And in a sense, it becomes the stronger the wiring is, the better we recognize the stimulus. And then it depends on what the visual information is. Again, if we're talking about vision, depends on what the visual information is, but it will then activate specific regions of the extrastriate cortex, memories of pictures, sounds, movements, spatial locations. They will then activate the appropriate regions in the sensory association cortex, and these regions again then become reinforced. The connections become stronger the more we are exposed to something, and the easier it is to then remember it. Sounds like I'm repeating the same thing a lot, but that's because the way learning works, it works in similar ways in the different systems. So it is a lot of repeating. The more exposure, basically, the better the wiring becomes. But in just a second, we're going to start talking about long-term potentiation and look at actually what's going on there. Before we get to that, let's talk about relational learning, and that's the last one of the learnings. Relational learning is essentially looking at the relationship amongst the stimuli. So when we're looking at things like the different systems of learning working together. Basically, as it says here, the relative location of objects, but you've got to recognize what an object is to recognize relative location. How our episodic memory involves remembering many different things, many different senses. So relational learning is basically going to be an integration. And the final thing I'll say with relational learning is that relational learning is one that we've actually learned what associations help us remember better. So if you want to remember something, one of the strongest associations we've found is associating things with happiness or pleasantness. Associating, if I give you a list of words and I ask you to associate each of those words with happiness in your mind, to find some link, and then later, like a day later, I asked you to recall those words, you'll remember that much better than many other associations. So that basically integration, we've learned what things connect better. So this is just kind of an overview of these different types of learning again. You've got the stimulus. Then you've got perceptual learning that comes with the perceptual system. And the changes in the neurocircuitry that happens with this perceptual system. Then you've got stimulus response learning that comes in the middle here before we get to motor learning. Motor learning, again, is going to happen in the motor system. And then finally you get the response. And then relational is going to be basically integrating all of this together into one. Any questions there? Let's get to the brain then. So long-term potentiation. So the rest of the time here we're basically going to talk about long-term potentiation and what's going on with it. Some of these we might go through relatively quick, but we're going to have some pictures, we're going to have some various different things that are going to look at what's going on. So again, long-term potentiation, the definition of it is an increase in excitability of neurons to particular synaptic input caused by repeated high-frequency activity of that input. So this is just a reminder of that definition of long-term potentiation. So basically, long-term potentiation is saying that repeated activity, and we're going to show the specific circumstances for that, but repeated activity causes the pairings to become stronger. And it's going to cause the pairings to become stronger because more receptors are going to form on the postsynaptic neuron. More receptors means that releasing those neurotransmitters into the gap, there's more sites for them to bind to, which means it's a higher likelihood of that postsynaptic neuron firing. And really what we're looking at here, there's two different systems. And the first is the NMDA receptors, or there's two different types of receptors that we're going to look at. The first is the NMDA. And this is basically when the neurotransmitters bind with the postsynaptic receptors located on an already depolarized dendritic spine. What am I saying then? Well, what I'm saying is you've got the terminal buds. And these terminal buds are releasing neurotransmitters. Okay? And then the postsynaptic neuron that maybe has other terminal buds going to it and all that, but the postsynaptic neuron, it's on the dendrites. If you'll recall, the dendrites are before the axon body typically. And then once enough gets in and the axon body fires, it then goes from that axon body down to the terminal buds on that secondary or the postsynaptic neuron. However, there's a thing that occurs when that happens. Something we didn't talk about when we talked about the initial. And that is when that axon fires, when that axon reaches its action potential. So when that axon fires, it goes to the terminal buds, but it also gives a backwash to the dendrites before it. So the dendrites that are before the axon body also become depolarized. It's a spike that goes backwards. I feel like I have to sneeze just because my mustache is tickling my nose. So when the axon fires, the dendrites also depolarize because this spike of activity goes back into the dendrites that are prior to the axon. If or when that happens, there are certain sites, the NMDA, and I'll show a visual of this in just a minute, but the NMDA sites actually release a blocker. These NMDA sites have a blocker in them. And when the depolarization occurs, they release a blocker. And glutamate can then bind to those sites because the blocker's gone. And this glutamate binding occurs within the cell that's already firing, and it's in a sense strengthening the connection. I told you it was coming. It's just, like I said, that mustache hair is just tickling the nose. Okay, so that firing occurs, and let's, like I said, we're going to look at some pictures. But the NMDA receptor, it controls an ion channel. But the calcium ions will only enter when glutamate is present when the postsynaptic neuron is depolarized. Like I said, I'll show a picture of it in a minute, but there's a blocker in the way when the postsynaptic cell is not depolarized. But when the axon fires and it basically kicks feedback into the dendrites, that feedback kicked into the dendrites is depolarizing it, and it's kicking out the blockers. When that blocker is kicked out, then the glutamate will bind to those receptors, which will open up an ion channel, a specific calcium ion channel, and that it's in a sense going to strengthen the synapse, because as we'll talk about in a minute, opening up that ion channel actually causes it to increase the amount of receptors on the postsynaptic dendrite. And this is what's called associative long-term potential, because the weakened synapse becomes strengthened. And this is how we get that with like classical conditioning, how you can have two different things paired. Well, the first one being there, if it's firing at the same time as the secondary cell's firing, even if it's not causing the secondary cell to fire, like with the Eyeblink response, if the tone is firing at the same time as the puff of air, the tone is causing glutamate to be released into the synaptic gap. That glutamate is then binding with the postsynaptic neuron because those glutamate sites have been freed up by the depolarization of the blink, because the blink happened because of the puff of air. And it then binds and causes more receptor sites. But like I said, we'll look at that. So here we've got it, and this is showing basically what's happening. There's a magnesium ion that's blocking the glutamate from binding. When the cell depolarizes, that is kicked out. The glutamate then binds, opens up the channel, and that's slightly incorrect way to explain it, because the glutamate binds either way. It's only when the depolarization occurs and the magnesium ion is kicked out that it opens up the channel, though. And by opening up the channel, as we're going to see on the next few slides, what happens after that. So this is something I've already said, but it's kind of another way to show it, is that when you've got this, the dendrite is already depolarized from a different cell causing it to be depolarized, the new one, the one that's not causing it to be depolarized, that still has connections to it, just weak connections, that allows those ion channels to open up, which strengthens the connections. And again, a visual representation of what I've already said, and that is that that residual activity from the axon firing causes the dendritic spike, because it's essentially going backwards to the dendrites. You've got the axon body, the axon potential is going down, but you still have that dendritic spike that comes back to the dendrites, depolarizing it and kicking out those magnesium ions, which is then allowing the sodium ion channels to open up and allowing in more sodium into those dendrites. I believe it's the next slide that's the important one. Nope, we're still two sides. But again, going back to our conditioned Eyeblink experiment, so we had that puff of air. That puff of air is activating the somatosensory neuron. The puff of air is activating the Eyeblink neuron. So you got puff of air. The puff of air has a connection to the Eyeblink, and the connection there is strong enough that enough neurotransmitters are being released that the Eyeblink occurs. The Eyeblink neuron fires. There's more to it than this, but this is the easy way to explain it is the puff of air causes the stimulus neuron causes the Eyeblink neuron to fire. Then the Eyeblink neuron firing has a dendritic spike that comes back up the dendrites, and it's releasing the blocker, and the tone neuron, the one that's associated with the tone, is firing at the same time. And again, it didn't have enough on its own to cause the Eyeblink, but it's firing at the same time. So because it's firing at the same time, it is binding with those dendritic spikes that are now open because of the depolarization. And by binding with it, as I will talk about in just a second, it's going to then, with the other types of receptors, it's going to form more receptors. I put a lot of slides in looking at this, and I still haven't even gotten to the other one yet. So again, the oxygen potential causes the receptors that are primed. The tone activates the auditory neuron. I've already explained all of this. I'll probably just delete this slide. Which gets us to the calcium that's entering through the activated NMDA receptor. And the calcium is then causing biological changes in the synapse that allows the connections to become stronger. The calcium that's going in is basically changing the postsynaptic neuron. The calcium isn't going in to change the polarization of the postsynaptic neuron. The calcium's going in and causing secondary changes, which cause these changes to the dendrites on the postsynaptic neuron. And essentially what they're doing is they're creating more binding sites so that it is more likely that this new neuron that didn't cause the secondary neuron to fire, the postsynaptic neuron to fire, to now cause it to fire. And this is basically, in long story, this is long-term potentiation. Long-term potentiation is essentially what I've been talking about here, where the strengthening becomes stronger when the unconditioned neuron, let's call them unconditioned and conditioned. The unconditioned neuron fires at the same time that the unconditioned stimulus does. Okay. Then we get that strengthening, and now we've got AMPA glutamate receptors. So once these ion channels are opened up and calcium moves into the cell, what it ends up doing is it causes a secondary reaction that causes the postsynaptic dendrite to form AMPA glutamate receptors, and these AMPA glutamate receptors then allow more glutamate to bind to it. They open up ion channels that does result in the potential for the postsynaptic neuron firing. This is one of the two pictures I have for what's going on here. But in this one, you see in A that you've got this postsynaptic density with the dendritic spine, the terminal button. It's releasing. It starts to bind in that way. It binds when the dendritic spike is depolarized, and it opens up other channels. And these other channels then are opened up, In B, you start to see them opened up. In C, they start to split. In D, they're split even more. And finally, in E, they just become extra dendritic spikes that are binding the two neurons. So what starts out as one dendritic spine turns into two. And this is just in one case, but what's really happening is you've got hundreds of spines that are splitting into double or more. So it's strengthening that connection. And this is the one that's the one I wanted you to see with the AMPA receptors. And in this one, first you get on the far left, you get that the NMDA receptor. It opens up because of the depolarization. The magnesium, the blocker is kicked out, which allows the ion in. The calcium ions then go in, and once they come in, they bind with certain receptors in the postsynaptic cell, and essentially they start a process of forming new receptor sites. And it goes through a series of steps. I could go into these in detail. You guys don't want me to go into these in detail. But in the end, that one site then ends up becoming multiple sites, multiple receptor sites. And now instead of one ion channel, you've got multiple ion channels. And since you've got multiple ion channels, it increases the odds of the presynaptic neuron, when it fires, actually causing the postsynaptic neuron the action potential to occur. Does that make sense? Go ahead.
So this makes sense, kind of, but I always forget like how the axon, how things travel down the axon, and then I'm wondering where is this taking place in the brain? Like if we can go out a little bit, so it's in the brain, in what part of the brain, and then I can't remember the way that the neurons travel.
And it's happening in all the different types of parts of the brain. So wherever you've got neural connections in the brain. Mainly for here, we're looking at like the somatosensory areas of the brain, but also the amygdala and various regions like that. But if you'll recall, you've got the axon body, you've got, this looks horrible, but you've got it like this, and then it comes off to terminal buds down here at the end. So the axon, it is a really ugly, it almost looks like an alien. But, so you've got the axon, terminals, and then the dendrites.
The axon body.
Yep, and the body's here. And the direction of the charge goes from the axon to the terminals.
Okay, that's helpful.
And as I was saying, what's going on here is when this fires, even though it's going to the terminals, it's also doing some kickback to the dendrites. And this kickback to the dendrites is what's opening up those blockers.
Got it.
So what's also occurring here is when those glutamate receptors, there's more glutamate receptors now. As a result of there being more glutamate receptors, it basically goes back to, it does feedback to the presynaptic neuron, which increases the release of glutamate in the presynaptic neuron as well. So now you've got more glutamate being released. You've got more glutamate receptors being present, and this is basically a reciprocal process that strengthens that neural connection. So again, going back to our Eyeblink example with classical conditioning, you have this, originally you have a puff of air. That causes an Eyeblink. But you pair that with a tone. So now a tone that didn't cause an Eyeblink, that tone is still firing at the exact same time that the Eyeblink is firing. That system causes more receptor glutamate locations glutamate receptor locations on the postsynaptic neuron of that gap and more glutamate to be released. So eventually, even if you don't have the puff of air, just the tone is causing that neural connection to fire, and you get the Eyeblink. And that is what is going on in the brain when classical conditioning is occurring. And it works for other types of conditioning. It works for operant conditioning as well. It works for other types of learning as well. But essentially what's going on is, and when we're looking at it with like operant conditioning, it's paired with that reinforcement. So what is going on there is it's just the way it's pairing in the brain. So all of these changes together, whether you've got the increase in glutamate receptors or the increase in glutamate release and the more dendritic spikes being formed, all of these together work in tandem to increase long-term potentiation, which means new neural connections are formed and things that weren't previously paired become paired. And that is all I have for you today. So last week we talked about memory, today we talked about learning, and even though I repeated myself a whole bunch, that's what's important when it comes to learning is that it's using very similar systems.